Hey, chemistry. We are going to talk today about a little bit more about isotopes and this concept of average atomic mass. So, we talked before about how the atomic mass of an atom is made up of the mass of protons and neutrons together. So, if you have an atom, like helium, for example, helium has two protons, it has two neutrons, and then it also has two electrons. So the mass of the atom of helium is going to be made up of the protons and the neutrons together. So the protons are going to weigh one each, so that'll give us two atomic mass units. The neutrons are going to weigh one each. That'll give us another two atomic mass units. Now, the electrons, we talked about, they do have mass, but the mass is so small that when you add it to the mass of the protons and the neutrons, it doesn't actually add any significant mass. It adds decimals. So if you keep the mass out to like the thousandths or the 10,000ths or the 100,000ths place, you'll eventually see the mass of the electrons. But if you round off to the tenths or the hundredths place value in your decimal, you're not actually going to see the mass of the electron. The electrons are what we say that they have negligible mass. So really, the atomic mass is going to come from protons and neutrons because the electrons' mass is negligible. So helium is going to have an atomic mass of four atomic mass units. Now, we can also measure this in grams. Helium has a mass in grams, and helium's mass in grams is due to its protons and its neutrons. The mass in grams, though, is a really small decimal, and so it's more convenient as chemists to deal in atomic mass units. So we've seen this. We've seen that the atomic mass comes from the protons and the neutrons together. However, when you look on the periodic table, you don't see a mass of 4 for helium. You see a mass of 4.0026 AMUs. When you see the mass of magnesium, for example, you don't see a mass represented by the 12 neutrons and the 12 protons, which would be 24. You see a mass on the periodic table for magnesium of 24.305 AMU. So throughout the whole periodic table, the atomic mass we see on the periodic table is actually a decimal. So the question is why? Why is atomic mass a decimal if it's just a mass of the protons and the neutrons together? Well, the answer lies in the fact that each element has more than one isotope. So just as a reminder, an isotope is the same atom or the same element. That means they all have the same number of protons. But they have isotopes of each other, have different masses. So the number of neutrons will actually change. So in an isotope, iso means the same, and that's referring to the same number of protons. But so it's the same element with the same number of protons, but different numbers of neutrons. So for helium, for example, we have one isotope of helium already drawn, 2 protons, 2 neutrons. Well, there are other isotopes of helium. There's an isotope of helium that weighs 5 AMUs, so 2 protons, 3 neutrons. Notice that the protons stay the same, the neutrons change, thus changing the mass without changing the element. And that is what an isotope is. So if we have these isotopes of helium, we have one that weighs 4, and we have another, well, let me draw it this way. We have a couple isotopes of helium. We have one isotope of helium that weighs 4. We have another isotope of helium that weighs 5. The question is, which one do we put on the periodic table? Do we put the isotope that weighs 4? So we put a mass of 4 on the periodic table, or do we put a mass of 5? Well, you can see what the makers of the periodic table decided to do. They decided to put an average atomic mass on the periodic table. And that's what brings us to today's lesson. Today's lesson, we're going to look at what that average atomic mass is and how that average atomic mass is calculated. Okay, so to start looking at this concept of average atomic mass, we're going to look at magnesium. So you can see here, here we have a picture of a strip of magnesium metal, and they've taken a piece of that magnesium metal and then they've blown it up. So it's almost like this little piece here is magnified, and these are all the magnesium elements that make up that little section of the magnesium strip of metal. Okay, so I want you to look at this. Another reminder here, when you're looking at the symbol of an isotope, you're going to see the symbol. You're going to see the mass in the top left corner. You may see the atomic number in the bottom left corner. Sometimes that gets included in the symbol, sometimes it does not. You will also see the charge in the top right corner if it has a charge. So if it has a charge, you'd see like magnesium 2+. You'd see a charge there. Or fluorine minus, you'd see a charge there. Now, for all of these elements, all of these atoms that you see in our strip of magnesium metal, what we have here is elemental magnesium. And elemental anything is always going to be neutral. So the number of protons equal the number of electrons. We don't have a charge. We don't have a net charge on these atoms. And so that is why you're not going to see a charge symbol in the top right for any of these. So the only thing that they include in all of these atoms for us in this drawing is the mass and the symbol. So you see magnesium and then you see the mass. Now I want you to look at the mass a little bit more closely. This would be a good time to pause the video and notice something. What do you notice when you look at all of these masses? And hopefully what you notice is most of them are magnesium 24. We have a lot of magnesium 24s in these drawings. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We actually have 15 of our atoms that we're looking at are magnesium 24, but there are other things present besides magnesium 24. What can you find? Now there are some magnesium 26s. Here's one. Here's another. Oh, I missed a magnesium 24. So I see 2 magnesium 26s, and I also found another magnesium 24. So I'm going to go 16 here. Okay, yet there is still more. Here we go. Here's a magnesium 25, and here's a magnesium 25. Okay, so what we have represented here in our strip of metal is 3 different isotopes. We have a magnesium 24, a magnesium 25, and a magnesium 26. Now, the majority of what we have here are magnesium 24s. We say that magnesium 24 is abundant, or the most abundant. If something is abundant, it's there in a very high quantity. You can say toilet paper is not abundant right now, right? It's nowhere to be found. So magnesium 24 is our most abundant isotope. Now, let's just pause here for a second and think. How many protons does magnesium 24, magnesium 25, and magnesium 26 have? How many protons are in each of these isotopes? This would be a good time to pause the video and write down your answer. And the number of protons for magnesium is always the same. Protons define the element you're talking about. So if you want to know how many protons the element has, you have to look at a periodic table. Magnesium has the atomic number of 12. Magnesium has 12 protons. So magnesium 24 has 12 protons. Magnesium 25 has 12 protons. Magnesium 26 has 12 protons, right? If it's magnesium, it has 12 protons. But 24, 25, 26 are not the same number. So the difference there is a difference in the number of neutrons. So magnesium 24 has 12 protons, 12 neutrons. How many protons and neutrons does magnesium 25 have? Yet another good place to pause the video and see if you can come up with an answer. And hopefully what you said is magnesium 25 has 12 protons and 13 neutrons. Magnesium 26 would have 12 protons and 14 neutrons. So 12, 13, 14 neutrons for all of these. And what we can do is write that out in a little equation to make it easier to follow. Okay, so magnesium 24 has 12 protons and 12 neutrons. Magnesium 25 has 12 protons and 13 neutrons, thus giving it the extra 1 in its mass. Magnesium 26 has 12 protons and 14 neutrons, thus giving it the extra 2 in its atomic mass. Okay, so all of this comes down to show that when you have an element, like we have a strip of elemental magnesium, you don't just have one isotope. Multiple isotopes naturally occur. And thus, we need to deal with the average atomic mass of these naturally occurring isotopes, and that's what gets averaged on the periodic table. So let's look a little more closely at the abundances of these isotopes. You're going to see two tables on the next page. I want you to look at the table on the top. Okay, so take a look at Model 2 here. So Model 2 here is talking about the 3 isotopes of magnesium. Here we go, magnesium 24, 25, and 26. And you can see here the atomic mass of each of these isotopes in AMUs. So magnesium 24 weighs 23.9850 AMUs. Magnesium 25 weighs 24.9858 AMUs. Magnesium 26 weighs 25.9826 AMUs. Now, this middle column here is the natural abundance of the element on Earth. Okay, so look at this. Magnesium 24, of all the magnesium that is found on Earth, 78.99% of that magnesium is magnesium 24. 10% of magnesium found on Earth is magnesium 25. And 11.0% of magnesium found on Earth is magnesium 26. So we see here that these abundances, these listed abundances for magnesium, correspond to what we saw in the image on the last page. Magnesium 24 is the most abundant. Magnesium 25 and 26 have about equal abundances. Remember, we had 16 out of our 20 total atoms was magnesium 24. 2 out of the 20 was magnesium 25. 2 out of the 20 in that image was magnesium 26. So it roughly lines up with what we saw in the image in the other page. Okay, so now the question is, how do we use this to calculate an average? So an average atomic mass, if I were to throw this out to you in math class, the majority of you would do this. You would add them all up, 23.9850 plus 24.9858 plus 25.9826. We'd add them all up. We'd divide by 3, right? And that would give us an average mass. So let's do that and see what we get. Okay, now when I do calculations and when I set up calculations, you will learn by watching me do it and following along with the answer. You will learn more if you try to do it and compare your answer to my answer. So a lot of the time when we are working together in chemistry, it's really easy to sit back and watch. That's not a great way to learn chemistry. So I want you to try this, pause the video if you need to, and calculate out an answer. See what you get. Okay, and I have my answer down here in the bottom, 24.9845. Notice Alan's method has set it up exactly how we have. He added the 3 isotopic masses divided by 3. The number of decimal places I'm going to keep, what I'm doing here is I'm matching what they had. So they kept it to the, 10,000th. They kept it to the 10,000th place. I'm going to keep my answer to the 10,000th place also. Okay, so 24.9845 is an average mass. That is legitimately an average mass. Is that the average mass that is written on the periodic table? No, it is not. The average mass written on the periodic table is 24.305 AMU. That is different than the average that we just calculated. So they must not be calculating their average in the same way we are calculating our average. And as you get deeper and deeper into math, and calculus and statistics and all of that good stuff, and you start to apply it to certain contexts, what you're going to see is there's a lot of different ways of calculating averages. And those different ways of calculating averages communicate different things. And so what the average on the periodic table is communicating is abundance. The average that they have on the periodic table is called a weighted average. And the average is actually weighted towards the isotope that is more abundant. Notice that the mass here, 24.3. Is that mass closer to 24, 25, or 26? 24.3 is closer to 24. It is closer to the element that is most abundant. And that's what a weighted average does. It takes your averages and it proportionately weights them towards certain things like abundances. Now, notice that the average that we just did also weights our average, but it weights it equally. Let me show you what I mean. If we take the equation that we just wrote and we distribute this 3, we can write 23.9850 times a third plus 24.9858 times a third plus 25, I'm running out of room here, 0.9826 times a third. Okay, all I did was I distributed that 3 that we're dividing by, right? third, a third, a third. So in the average, basically we're taking a third of everything and averaging and adding them together so that we get one whole thing. You can also, instead of multiplying by a third, you can multiply by 0.33 repeating, also known as 30%, right? Or not 30%, 33 repeating percent. Okay, so basically we're taking 33% of each of these things and we're averaging them together. So that percent that we're taking of each piece of information is our weight. We are taking an equal amount of all three things. So what if instead of taking an equal amount, instead of taking 33.3 repeating percent of each of them, I took the abundance of each of them. So I'm going to do 78.99%, which in decimal form is going to be 0.7899. Okay, so instead of taking 33.3% of each of them, I'm going to take the natural abundance of each of them. 0.1000. So this would be the 10.00%. And this is going to be the 11.01%. So 0.1101 goes there. Okay, so I'm going to do the average again, but I am going to use the percent abundances instead of using an equal percent for all three. And I'm going to calculate an answer. Let's see what I get. 23.8850. Okay, again, this would be a great time to pause the video, do this calculation yourself, and see if you can get the right answer. Setting up the problem is half of the challenge here. Plugging it into your calculator is the other half. Okay, so let's double check our calculator skills here. Okay, and what I got was 24.2, what are we keeping it to? So these keep it to the 10,000th place. These only keep it to the 100th place. So I'm going to keep this to the 100th place. 0.23 AMU. Okay, so it gives us a different answer. Let's compare this. 24.98% when each of the portions was 33%. 24.23 AMU when each of the portions was the natural abundance on Earth. Okay, and you can see, so this is what's called a weighted average. We've taken an average again, but instead of using an equal proportion for each thing we're adding into the average, we're taking a weighted proportion of each thing that we're adding into the average. Now notice all of our decimals still add up to one whole thing. And that's very important in order to actually have an average. Okay, so with that in mind, that is what a weighted average is. I want to take a minute and I want to look at Mary's method and Jack's method. Both Mary and Jack have done a weighted average. What's the difference in how they did their weighted average? So go ahead, take a minute, pause the video, and see if you can figure out a difference between Mary and Jack's method. Okay, in Mary's method, what you'll see here is her abundances, she uses the actual percentage, 11.01%, 10.00%, 78.99%, and she ends up dividing by 100 before she gets her answer. Jack's method does not use the percent form. Jack's method uses the decimal form. Notice he doesn't use 78.99%. He uses 0.7899. He's using the decimal form. Decimal form 0.1000, decimal form of 0.1101. But both of them are going to get the same answer of 24.23. 24.2. Oops, that's a 2, 3. Either way you do it, you're going to get the same answer. The percentage point divided by 100 is the same as the decimal point form. So you can use either method to calculate your weighted average. Now notice that this weighted average is much, much closer to that listed atomic mass on the periodic table. That listed atomic mass on the periodic table is 23.40. The weighted average that we just calculated is 24.23. So it's much closer than using the average that we initially calculated, Allen's method. Okay, this is a weighted average for the average atomic mass of an isotope. I do want to look at one practice problem together, and then you guys can go practice on your own. Okay, here we go. So you're going to use one of the methods in Model 3 that gave the correct answer for average atomic mass to calculate average atomic mass for oxygen. Isotope information is provided below. Show all of your work and check your answer against the mass listed on the periodic table. This would be a great time to pause the video and see what you get. All right, so I am going to take the mass times percent abundance for the first isotope plus mass times percent abundance for the second isotope plus mass times percent abundance for the third isotope. That's the format that I am going to calculate with a weighted average with. All right, I have mass times abundance plus mass times abundance plus mass times abundance. Okay, and the answer that I get from this is 15. Okay, so they keep it to the thousandths place here, keep it to the hundredths, so I'm going to keep it to the hundredths. 0.99. If I kept going, let me just tell you what my calculator has for comparison. That's what my calculator is displaying. Okay, and we're going to go to the periodic table. And the listed mass for oxygen is 15.999. So we came out right there. We have 15.999. If you round that to the hundredths place, you're going to end up with 16.00 AMU. All right, I hope you got the same answer too. Let me know if you have any questions. Now, this is something that is in your book. I want to make sure you know where it is. It can be a confusing topic. And so, like many things in chemistry, the more ways you see it explained, the more you're going to understand it. So if you want to reread through somebody else's explanation, this is in 4.3 in our book. Let's see, there's practice problems 23 and 24. Those can be found on page 117. And there are thousands of other chemistry teachers, chemistry students, chemistry tutors online who will also provide you with videos or simulations or worksheets for this weighted average. Practice this problem. Read as many different explanations as you need to feel comfortable with this, and practice this problem until you can do a weighted average problem from start to finish without having to ask questions or look up resources. And then you can be confident that you are going to be able to do this problem. So great job. Again, let me know if you have questions. I'll see you in class.